Hello YouTube. So given that alpha is a real number greater than 0, what is the following limit? Alright, so the crux of the problem is actually that there are three different cases for alpha, and depending on which case, you'll get a different result. So the first case that we'll be solving for is when alpha is in between 0 and 1. The second case will be if alpha is equal to 1. And the third case is if alpha is greater than 1. So let's just start with this one. Alright, so let's cover case 1 where alpha is in between 0 and 1. So in order to start, let's expand this sum. So by expanding the sum, we get something that looks like this. 1 over n plus 1 to the alpha plus 1 over n plus 2 to the alpha plus 1 over n plus 3 to the alpha, and so on until we get to 1 over n plus n to the alpha. Okay, so in this problem, I'm going to use the squeeze theorem, and the reason why will make sense later. But in order to do the squeeze theorem, we must establish a lower and an upper bound, and both the lower and upper bound expressions must converge to the same limit for this to also converge to the same limit. So first of all, let's just establish a lower bound, a particularly helpful lower bound. So first of all, we know that k, which is the base of this exponent, is in between 1 and n inclusive. And we also know that alpha is positive. So this implies that k to the alpha is always equal to or less than n to the alpha, and consequently 1 over n plus k to the alpha must always be equal to or greater than 1 over n plus n to the alpha. So that's just some easy algebra, and because we know that, then we know that every single one of these terms must be equal to or greater than this guy over here. So this term is equal to or greater than this term is equal or greater than this, and so on all the way to this one. And equality falls under the umbrella of this type of inequality. So this is also equal to or greater than 1 over n plus n to the alpha. So since we have n different terms all equal to or greater than 1 over n plus n to the alpha, we have n times 1 over n plus n to the alpha. So we establish a lower bound. Cool. Now we also have to establish a particularly helpful upper bound. So let's do that. So first of all, we know that, well, 1 over alpha is equal to 1. So that's pretty simple. And we know that since k is in between 1 over 1 and n inclusive, we know that then that 1 over alpha is always equal to or less than k to the alpha, right? So then in other words, 1 over n plus 1 to the alpha, or just 1, is equal to or greater than 1 over n plus k to the alpha. Now that's the more simple algebra. Now, just like the same logic from last time, if we know that this is less than 1 over n plus, less than or equal to 1 over n plus 1, this one is also less than or equal to 1 over n plus 1, and we get n terms all equal to or less than 1 over n plus 1. So then we can say that this entire sum is bounded above by 1 over n plus 1 times n. So we all have n terms all equal to or less than 1 over n plus 1. Okay, so now let me just erase that. We have some very nice lower and upper bounds, and the reason for that is because if we set the limit as n goes to infinity, well, let's try that. So limit as n goes to infinity of n over n plus n to the alpha. Well, this might not seem straightforward, but it is, because we know that alpha is less than 1. And because we know alpha is less than 1, we know that this n dominates over this n to the alpha term. N to the alpha is a weaker term, so this is just equal to limit of n to infinity of n over n. Because n to the 1 power dominates over this, and so this is 1. Okay, so that's fine. We know that this approach is 1, so I'll just label this as 1. And we know that, well, limit of n goes to infinity of n over n plus 1, that obviously is 1. I don't need to give any further explanation, so this one also I'll label as 1. So since we know that the limit as the lower and upper bound goes to 1 as n goes infinity, then by squeeze theorem, the sum must also go to 1. So this is case 1. But there's 2 more cases to consider, so let's move on to the next case. Alright, so case 2, which is alpha is equal to 1. Well, okay, let's try it. So limit as n goes to infinity of summation of n k equals 1 of 1 over n plus k to the alpha. Alpha is 1, so we just have this. Now, we can rewrite this in a certain way that will be particularly favorable to us. So limit as n goes to infinity of infinite sum n k equals 1, and then now what we'll try to do is we'll say we'll have 1 over n times 1 divided by 1 plus k over n. So now this looks awfully like a Riemann sum, the summation form of a Riemann integral. So if you just remember from your basic calculus class, you'll know that this is actually just equivalent to the Riemann integral from 0 to 1 of, so this would be your dx, this would be your dx or delta x, and this would be 1 over 1 plus x. So this would be the Riemann integral from 1 over 1, from 0 to 1 of 1 over 1 plus x dx. And this is pretty solvable, because if you just do that, you'll get ln of 1 plus x, lower bound, upper bound, 0, 1. And this is just equal to ln of 2. Alright, so let's cover case 3 where alpha is greater than 1, and I think this is arguably the hardest case to cover. So, just a spoiler, we want to show that this approaches 0, and we want to use a squeeze theorem again. So, we can obviously establish 0 as a lower bound, because we know every single term in this sequence is going to be positive, so let's expand the sequence out and get something like this. And so on until we get 1 over n plus n to the alpha. And now we want to bound this sum from above with something, with a term that approaches 0 as n goes to infinity. But how the hell do we do that? Because that's the tricky part. Well, let me just start with a seemingly unrelated fact. So it's known that square root of n minus k to the alpha over 2 power squared is always equal to or greater than 0, because any real number squared must always be positive. Okay, fine. So then let's expand it out. We get n minus 2 root n, k to the alpha over 2, plus k to the alpha is equal to or greater than 0. So then we know that n plus k to the alpha must be equal to or greater than 2 root n, k to the alpha over 2. And because we know this, we know that the reciprocals must have the exact opposite inequality. Well, what do you know? This inequality applies to each term in this sum perfectly. So let's apply it. So we have 1 over 2 root n factored out. And well, for the first term, well, k equals 1, so this can apply directly to here. So we have 1 over 1 to the alpha over 2. And then for this term, we have, well, k equals 2. This can apply here, so 2 alpha over 2. And this goes so on until we get to n, the nth term. So now we have something that might be useful. We have an upper bound. We don't know if it approaches 0 yet, but we'll show that in a little bit. So let me just erase this. Now we have 2 more subcases that we'll consider. So the first case, which is particularly easy, is if alpha is greater than 2. So if alpha is greater than 2, then we are now considering the limit of 1 over 2 root n of summation k equals 1 to n of 1 over k to the alpha over 2. And because we know that this is constant, so this can be outside of the summation. Well, if alpha is strictly greater than 2, then the p-series test will show that this sum converges. And if this sum converges, then this is equal to some finite number where L is less than infinity. This is just notation for L being finite. So if L is finite, then we have limit as n approaches infinity of L over 2 root n. This is equal to 0. Okay, so we have then that if alpha is greater than 2, then the limit, we have 0 for the limit. But that's not so helpful because we want, well, what's in between 1 and 2. That's a lot trickier, so let's cover that. Ooh. So if we have alpha being in between 1 and 2, well, things get a lot trickier because, well, now we have limit n goes to infinity of the summation k equals 1 to n of 1 over k to the alpha over 2 divided by 2 root n. But the thing is, now the p-series test will show that this diverges because alpha over 2 is going to be less than 1. And because alpha over 2 is less than 1, well, the whole sum must diverge to infinity. Since this is strictly positive, so this must go to infinity. So this goes to infinity. Obviously, square root of n as n goes to infinity is infinity. So we have an indeterminate form. Great, that's not what we want, but we can still make do with this. So to make use of the information that we got, which was that we have the numerator and the denominator both approaching infinity, we have to use a lemma called the Stolz-Cesaro Lemma, and we're just going to use one case of it, not the general case. So what a restatement of the lemma can tell us is if the sequence b of n is monotone, in our case, strictly increasing to infinity, and we also have a of n going to infinity as well, and limit as n goes to infinity of b of n, a of n plus 1 minus a of n over b of n plus 1 minus b of n approaches a finite number L, then the limit of a of n over b of n approaches that same finite number L. So our new goal is going to be proving that this limit over here exists. And if this limit over here exists, then this limit must go to the same exact number. Right, so in order to make use of the Stolz-Cesaro lemma, we need to define a numerator sequence and a denominator sequence. So I'll do exactly that. We define a of n as the sum from 1 to n of 1 over k to the alpha over 2. So, and then we define the denominator sequence as just 2 root over n, or 2 root of n. And so naturally, by the p-series test, this will diverge to infinity. By just looking at b of n, it diverges to infinity. So we have the indeterminate form that we want. We can apply this the lemma. So first of all, let's find a of n plus 1 minus a of n. So I'm just going to write it out, but this difference should be pretty obvious. And as you can see, these two sums, the only difference is the n plus 1th term of this sum over here. And the thing is, the k equals 1 to n, all the terms will cancel out between these two sums. The only thing left is just the n plus 1th term, so we have here. And then b of n plus 1 minus b of n, well, that's pretty easy. That's just 2 times root of n plus 1 minus root n. So let me just erase this. We'll have 1 over n plus 1 to the alpha over 2 power. Okay, so now we take the ratio between these two, set the limit as it goes to infinity. So we have 1 over n plus 1 to the alpha over 2 divided by 2 times root n plus 1 minus root n. Now we can multiply the conjugate, so we can multiply n plus 1 plus root n divided by root n plus 1 plus root n to the numerator denominator. So then you know the bottom term by difference of squares would just end up turning to 1. So we would end up with a of n plus 1 minus a of n, b of n plus 1 minus b of n equaling, well, since the bottom term just goes to 1, we just get 2 times 1 the denominator, and then we can place this into the denominator, so we have n plus 1 to the alpha over 2 power, and then we can have this in the numerator, so we get square root of n plus 1 plus root n. Okay. So as we take the limit as this goes to infinity, or as n goes to infinity, well, okay, so we know that alpha is greater than 1. It's greater than 1, okay? So, in other words, alpha over 2 is greater than 1/2. Now, the degree of the numerator is exactly 1/2, but the degree of the denominator is greater than 1/2. Because of that, the limit is 0. That's just standard calculus. So because we know this, then we technically know that this approaches 0. And so we know that this ratio exists. And because it exists by the Stolz-Cesaro lemma, we get that limit as a of n over b of n exists as well. And it converges to precisely the same thing, which is 0. Therefore, so let me just erase all this. We get that this approaches 0 as n goes to infinity. And obviously 0, the constant, also goes to 0 as n goes to infinity. So by squeeze theorem, so I'll just call it ST, this must also go to 0 as n goes to infinity. Okay, so then we can conclude that the limit as n goes to infinity of this sum is actually a piecewise function. So it's actually equal to 1 if alpha is in between 0 and 1 non-inclusive. It's ln of 2 if alpha is equal to 1, and it is 0 if alpha is greater than 1.